So this is what Theodorsen did, but like I said, Theodorsen played in the cylinder domain. So in the cylinder domain, Theodorsen had source distribution on the upper surface, Q as a function of theta, and this is per unit length, okay? Distribution. Right here we have also sink in the same string. So this is negative Q of theta per unit length. So we have a distribution of this guy on the upper surface and lower surface. Okay? Q is what? Q is unknown or known? What do you think? Q is what? Unknown. Any idea how to determine Q in general from the global overview? We usually assume singularities. Okay, how to determine this singularity? What's the equation that helps you to determine the singularity? In general, the overview. I mean, we can go through the details and we will go, but you have to have some expectation from the beginning. How are you going to get this singularity? What's the equation? I mean, there is nothing more. Here are your formulation, nothing out of these. This is the entire potential flow thing. Don't think out of these. All the models that are developed in the 30s and 40s, they are simply shuffling these. Maybe start here and then apply this second and third, maybe the other way around, but it's nothing out of this box. How are you going to determine your singularities? What equation will help you? I'm sorry? No. And why is no? Because the Dakota condition here, we're talking about non-circulatory flow. There is no circulation. The Dakota condition is not that useful. Well, whenever you introduce singularities, like we did in the thin airfoil theory last week, we just use the no penetration boundary condition to get the corresponding equation, and that's it. So this is our expectation: is to get the no penetration boundary condition to get this guy from me. But anyway, don't lose our goal. Our goal is to get the tangential velocity Vt. Okay, we said let's get the tangential velocity. Okay, Theodorsen, how are we going to set up the problem? Set it up into non-circulatory and circulatory. For the non-circulatory has source distribution, which means that I need to get my V theta in terms of this source distribution. So let's get that. We will do it in detail, so please be patient. So we have some source distribution here that is Q, this is B over 2, the radius, okay? Q at an angle phi times the length element, which is R d phi. The radius is simply B over 2. Now we have the exact same thing here, but negative Q phi B over 2 d phi, okay? This is the same angle. And I have a generic point here at a distance R and an angle theta. So this is zeta equals R e to the I theta. And I want to get the radial and tangential velocity. In particular, I'm interested in the tangential velocity, right? So let's get that. How we do it? Anybody can tell me how to start? So I want to get the velocity at this point due to this pair. Any idea how to start? Suggestion? Come on. This is the main point of potential flow, is that you know the solution to each one individually, simply add them. It's that simple. So we know something called the complex potential due to a source. What is the complex potential due to a source? Well, it's Q over 2 pi ln Z. So it's Q, here is your Q, over 2 pi ln zeta. But this is assuming the source at the origin. If it's not at the origin, just subtract its location. Its location is at V over 2 e to the I phi, correct? This is due to the source. And I will add the one due to the sink. It's the exactly same thing, but with negative Q, right? Ln zeta minus what? Zeta minus what? Come on guys, you will have, this stuff will be available, right? You don't need to indulge in writing without getting the point. What's this? I mean, you will have, there is a homework problem that you will turn on Wednesday and it needs this thing. So we'll do some training together. What should I write here? What should I write?
Conjugate?
Sorry?
It's minus I theta.
Yeah, b over 2 e to the negative I phi. Any question about that? So you got the complex potential. How to get the velocity? Well, the velocity, complex velocity is df by d zeta. This is easy. Again, it's q b over 2 d phi over 2 pi times 1 over z minus 1 over z minus b over 2 e to the I negative 1, which is q b over 2 d phi over 2 pi. You subtract, so this guy minus that guy, zetas go away, you have b over 2 e to the I phi minus e to the negative I phi divided by zeta times zeta minus b over 2 e to the negative I phi. So like I said, we'll do it in detail, so please be patient, but also pay attention, because you will do homework, you will do midterm, and you will need to, you know, do this kind of stuff. And there will be some tricks that we will show. You will need to use these tricks in the midterm. So please pay attention. What's this guy? What's this guy? Yep. 2I sine phi. Very good. Thank you. And downstairs we'll multiply, so I'll have zeta squared minus b over 2 zeta e I phi plus e negative I phi plus p squared over 4. Okay? And zeta, what is zeta? Zeta is any generic point r e to the I theta. So this is again q b squared over phi d phi b squared over 4 2 pi 2i sine phi r squared 2i theta b over 2 r e I theta, and similarly this guy is 2 cosine plus b squared over 4. Okay, this is the complex potential, and at the end of the day I need the radial and tangent. It depends on what you need. If you need the u and v, real and imaginary, then try to get this in real and imaginary. But what I need is radial and tangential. Well, this is written in terms of radial and tangential as negative I theta Vr minus I v theta. So I need to create e to the negative I theta, and whatever left, I will get its imaginary part. This is v theta that I'm looking for. So I will multiply up and down by e to the negative I theta. So I have w equals qb squared over 4 d phi 2 pi e to the negative I theta here. Down now we have r squared e to the I theta r 2 cosine phi p squared over 4 e to the negative I theta. So again, from this guy, I created the e to the negative I theta. Whatever left here, I need its imaginary part. So I will have the denominator, have its real as imaginary, multiplied by the conjugate, all this kind of stuff.